Students, and welcome to today's lesson. I'm Mrs. Levine. Today, we will continue to explore the question, what causes a moving object to slow down and stop? Are you ready? Grab your pencil and your science journal and let's get started. Imagine you're outside on a golf course that looks like the one in this photograph. What do you notice about the materials that make up the surface of the golf course? I notice a few different types of materials. I see sandy areas, but I also see a lot of green grass. The grass around the flag looks like it is cut very short, but the grass farther away from the flag looks rougher and thicker. Why do you think golf courses use different surface materials? Maybe the different materials cause the golf balls to slow down and stop at different distances, like the materials we tested in our investigation. Today, we'll analyze and interpret the data from our investigation to see what else we can learn about how different materials can affect the distance a ball travels. Here's the data table from our investigation. Can we find some patterns? Finding patterns just by looking at the data table is a little hard. Do you agree? I know. Maybe we can graph our data. Scientists often graph data to look for patterns to help them analyze the results of an investigation. Oh, remember when we used a line plot to help us analyze the data from our car investigation? Let's draw a line plot for this data too. Let's start with the burlap first. I created a line plot for us. I used the shortest and longest distances as endpoints for our line plot. Then I added a tick mark for the distance between the endpoints. Each X shows the data from our 4 trials for burlap. Now we can analyze our results. Let's find a typical distance value. This number is the value that best represents the distance the ball traveled on burlap. How can we find the typical distance value? Well, which of these values are not the best representations of the data? Even though there are 2 X's above 45 centimeters, those tick marks are all the way at the end of the line plot. That distance does not really represent all of the data in the line plot. So which distance best represents the data set? Point to the distance on your screen. In this case, choosing a distance in the middle makes the most sense. So 44 centimeters best represents the data set because it's right in the middle of the values. Here's our line plot for the rubber padding. Like the last line plot, I used the shortest and longest distances to create the endpoints for this line plot. Since there are only 2 distances recorded for the rubber padding, we only have 2 distances on our line plot. Let's look at the number of X's above each distance. I see 3 X's above 59 and only 1 X above 60. So which distance best represents the data set from the rubber padding trials? 59 centimeters is the most common distance and also the best representation of the data. We have one more line plot, the artificial grass line plot, to look at. Just like the last 2 line plots, I used the shortest and longest distances to create the endpoints for this line plot. Which distance best represents the data set? Shout it out! 15 centimeters is the most common distance and also the best representation of the data. I added a column with our typical distances for each material we tested. Now let's use the typical distances we found to look for relationships between the material and the distance the ball travels. What do you notice about the materials? Both the burlap and the rubber padding have smooth surfaces, while the artificial grass is rough. Hey, do you see a connection between the material's texture and the distance the ball travels? Our investigation seems to show that the rougher the material, the shorter the distance the ball travels before it stops. So what is the relationship between the material and the typical distance the ball travels? The ball travels much farther on smoother materials such as the burlap and rubber padding than on rougher materials such as the artificial grass. What does this relationship tell us? The motion of the ball changes when it slows down and stops, so some force must slow the ball down on every material. Maybe the force is stronger for rougher materials. Hold on, I need a quick review. What forces act on the ball as it rolls? We talked about this in our anchor model when we looked at a soccer ball rolling across grass. We found out that gravity exerts a downward force on the soccer ball as it rolls, and the ground exerts an upward force or push on the soccer ball as it rolls. That information is also true for this golf ball. So for an explanation, we can say gravity pulls the ball down and the ground exerts an upward force on it. So we know what forces act on the ball when it's moving, but what force do you think causes the ball to slow down? I don't think gravity causes the ball to slow down because the ball isn't falling. And the upward force from the ground doesn't cause the ball to slow down because the ball isn't moving up. I think that gravity and the upward force are balanced. What does that tell us about the forces acting on the ball? Since gravity and the upward force are balanced, another force must be pushing the ball in the direction opposite to its motion. Yes, there is another force. That force is called friction. Friction is a force exerted between the surfaces of objects in contact. The surface of the ball is in contact with the different surfaces it rolls across. The force between the surface of the ball and the surface of each material is friction. Friction causes the ball to slow down and eventually stop. So how did the friction acting on the ball compare for each material we tested? Let's look back at our data. On which surface was the force of friction the weakest? The ball rolled the farthest on the rubber padding, so the force of friction wasn't very strong at all. On which surface was the force of friction the strongest? The force of friction was strongest for the artificial grass since the ball stopped at the shortest distance on that material. Great! Now that we've learned about another force, let's add friction to our force model. Which way should we draw the arrow? Well, friction is opposite to motion. In our model, the motion of the ball is going this way, so friction must be acting in the opposite direction. Let's also write an explanation for our model. We already know that gravity pulls the ball down and the ground pushes it up. We can add that friction acts in the opposite direction of the ball's motion. The forces acting on the ball are unbalanced, which causes the ball's motion to change. It slows down and eventually stops. Wow, we've learned so much about what causes a moving object to slow down and stop. Your task today is to answer a question about what causes a moving object to slow down and stop. Hey, I wonder if there's a connection between the different materials on the golf course and friction. I think the short grass, the longer grass, and the sand all exert different amounts of friction, so the ball travels differently across each material. Playing on different surfaces with different amounts of friction probably makes it hard to get the ball to stop where you want it to. Golf must be a tricky game to play. You know, in our investigation, we saw how a ball rolls down and stops, but I wonder what causes the ball to stay at rest after it stops. We'll need to do some more exploring in our next lesson. Let's review your task for today. Your task is to answer the question about what causes a moving object to slow down and stop.